To calculate the motor branch circuit for three-phase motors rated at 1000 horsepower or less, you can use the following formula: full load amperage equals horsepower times 746 divided by efficiency times voltage divided by the square root of 3 times power factor. In this formula, horsepower is the motor horsepower rating, efficiency is the motor efficiency expressed as a decimal, voltage is the motor operating voltage, and power factor is the motor power factor expressed as a decimal. Now, consider a 20 horsepower motor operating at 208 volts. Let us assume an efficiency of 0.9 and a power factor of 0.85. Using the formula, the full load amperage equals 20 times 746 divided by 0.9 times 208 divided by the square root of 3 times 0.85, which equals approximately 74.6 amps. This calculation provides the full load amperage, which is essential for determining the appropriate wire size and protection for the motor circuit. Now let's move on to the branch circuit calculation. The running load amperage for the example motor is 74.6 amps, as calculated previously. The starting current is given as 166 amps. To account for the inrush current during startup, apply the 125% rule to the starting current. Circuit current equals starting current times 1.25, which equals 166 amps times 1.25, resulting in 207.5 amps. Using the calculated circuit current of 207.5 amps, you can determine the appropriate wire size and conduit size according to the National Electrical Code, also known as the NEC. Remember that this formula does not include the starting peak current, which can be significantly higher than the starting current. In some cases, a reduced voltage starter or other starting method may be necessary to mitigate the high starting peak currents. It is always recommended to consult with a qualified electrician to ensure proper motor branch circuit design and installation. This helps to ensure safety and compliance with electrical codes. The formula provided is a fundamental tool for electrical engineers and electricians involved in motor installations. It helps to ensure that the motor operates safely and efficiently within the design parameters. The key parameters in the calculation include the motor's horsepower, voltage, efficiency, and power factor. Understanding these parameters is crucial for accurate calculations. The 125% rule is a safety factor applied to the starting current to accommodate the temporary surge of current when the motor starts. This helps to prevent nuisance tripping of circuit breakers or fuses. The NEC provides detailed tables and guidelines for selecting the appropriate wire size and conduit size based on the calculated circuit current. Adhering to these guidelines is essential for ensuring the safety and reliability of the motor circuit. Reduced voltage starters are often used to limit the starting peak current, which can reduce stress on the electrical system and prevent voltage dips. Consulting with a qualified electrician is always recommended to ensure that the motor branch circuit is designed and installed correctly, taking into account all relevant factors and codes. In summary, calculating the motor branch circuit involves determining the full load amperage, applying the 125% rule to the starting current, and selecting the appropriate wire size and conduit size according to the NEC. It is important to consider the start and peak current and use appropriate starting methods if necessary. Always consult with a qualified electrician for assistance. The efficiency of the motor is a critical factor in the full load amperage calculation. A higher efficiency means that the motor will draw less current for the same amount of output power. The power factor is a measure of how effectively the motor uses electrical power. A higher power factor means that the motor is using electrical power more efficiently. The square root of 3, approximately 1.732, is used in the formula to account for the phase relationship in a three-phase electrical system. The full load amperage calculation is based on the assumption that the motor is operating at its rated horsepower and voltage. The starting current is typically several times higher than the full load amperage. The 125% rule is intended to provide additional protection for the motor circuit during startup. The NEC specifies the minimum ampacity of the conductors in the motor branch circuit. The conduit size must be large enough to accommodate the conductors and any necessary grounding conductors. The starting peak current can be significantly higher than the starting current, especially for motors with high inertia loads. Reduced voltage starters, such as auto-transformers and part-winding starters, can be used to limit the starting peak current. Other starting methods, such as variable frequency drives, can also be used to control the motor's speed and torque during startup. It is important to consider the ambient temperature when selecting the appropriate wire size, as higher temperatures can reduce the ampacity of the conductors. The NEC provides correction factors for adjusting the ampacity of conductors based on the ambient temperature. It is also important to consider the voltage drop in the motor branch circuit, as excessive voltage drop can reduce the motor's performance. The NEC provides guidelines for limiting the voltage drop in motor branch circuits. Grounding is an essential safety measure for motor branch circuits. The grounding conductor must be sized according to the NEC. Overcurrent protection, such as circuit breakers or fuses, must be provided to protect the motor branch circuit from overloads and short circuits. The overcurrent protection device must be sized according to the NEC. Short circuit protection is important to protect the motor branch circuit from high fault currents. The short circuit protection device must be sized according to the NEC. Proper coordination of overcurrent and short circuit protection devices is essential to prevent nuisance tripping and ensure the safety of the electrical system. Motor control centers are often used to house the motor starters, overcurrent protection devices, and other control equipment for multiple motors. Motor control centers provide a convenient and organized way to manage and control motors in industrial and commercial applications. Variable frequency drives, also known as VFD, can be used to control the speed and torque of motors. VFD can also improve the energy efficiency of motor systems. Programmable logic controllers, also known as PLC, can be used to automate the control of motor systems. PLC can be programmed to perform a variety of control functions, such as starting and stopping motors, controlling motor speed, and monitoring motor performance. Proper motor branch circuit design and installation are essential for ensuring the safe and reliable operation of motor systems. The NEC provides detailed guidelines for designing and installing motor branch circuits. Consulting with a qualified electrician is always recommended to ensure that the motor branch circuit is designed and installed correctly, taking into account all relevant factors and codes. The motor's nameplate provides important information about the motor's characteristics, such as its horsepower, voltage, full load amperage, efficiency, and power factor. This information is essential for designing the motor branch circuit. The motor's service factor is a measure of the motor's ability to handle overloads. A higher service factor means that the motor can handle larger overloads without overheating. The motor's insulation class indicates the maximum temperature that the motor's insulation can withstand. The NEC specifies the minimum wire size for motor branch circuits based on the motor's full load amperage and the type of insulation used. The NEC also specifies the minimum conduit size for motor branch circuits based on the number and size of the conductors in the conduit. The NEC provides tables for determining the ampacity of conductors based on their size, insulation type, and ambient temperature. The NEC also provides tables for determining the conduit fill based on the number and size of the conductors in the conduit. It is important to select the appropriate type of conduit for the motor branch circuit based on the environmental conditions and the type of installation. Common types of conduit include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and flexible metal conduit. Grounding is an essential safety measure for motor branch circuits. The grounding conductor must be connected to the motor frame, the metal conduit, and the equipment grounding bus in the electrical panel. Overcurrent protection devices such as circuit breakers and fuses must be sized to protect the motor branch circuit from overloads and short circuits. The overcurrent protection device must be rated to interrupt the maximum fault current that could occur in the motor branch circuit. Short circuit protection devices, such as fuses and circuit breakers with instantaneous trip elements, must be sized to protect the motor branch circuit from high fault currents. The short circuit protection device must be rated to interrupt the maximum fault current that could occur in the motor branch circuit. Motor starters are used to start and stop motors and to provide overload protection. Motor starters typically consist of a contactor, an overload relay, and a control circuit. The contactor is an electromechanical switch that is used to connect and disconnect the motor from the power supply. The overload relay is a protective device that is used to protect the motor from overloads. The control circuit is used to control the operation of the contactor and the overload relay. Variable frequency drives, also known as VFD, are used to control the speed and torque of motors. VFD can also improve the energy efficiency of motor systems. VFD work by converting the incoming alternating current power to direct current power and then converting the direct current power back to alternating current power at a different frequency. By varying the frequency of the alternating current power, the speed of the motor can be controlled. Programmable logic controllers, also known as PLC, are used to automate the control of motor systems. PLC are small computers that can be programmed to perform a variety of control functions, such as starting and stopping motors, controlling motor speed, and monitoring motor performance. PLC are often used in industrial applications to control complex motor systems. Proper motor branch circuit design and installation are essential for ensuring the safe and reliable operation of motor systems. The NEC provides detailed guidelines for designing and installing motor branch circuits. Consulting with a qualified electrician is always recommended to ensure that the motor branch circuit is designed and installed correctly, taking into account all relevant factors and codes. Remember to always consult the latest edition of the National Electrical Code and local regulations for the most up-to-date requirements. The information provided here is a general guide and should not be considered a substitute for professional electrical engineering advice. Always prioritize safety and compliance when working with electrical systems.